Okay, so for each of these limits, we're asked to determine the limit graphically and confirm algebraically. So graphically just means grab a graphing calculator. And if you're typing this in a TI, you don't want to use T, you want to use X, right? So you'll need parentheses, and then divide it by this in parentheses. So that's how you'd want to type this into a TI calculator. But I'm on a computer, so for time I'm going to plug this in Desmos. That's the music I listen to while I'm working, I guess. T squared minus 3t plus 2. So I'm going to type in a fraction. And it was t squared, so I'm going to use x squared for Desmos. Minus 3x plus 2. And that's all over x squared minus 4. Or t squared minus 4, either one. Okay, so that's what it looks like graphically. We're supposed to evaluate the limit as x approaches 2. So if you look at the graph, where is, so t approaches 2, or x approaches 2, in other words, for the way I've changed the variables. So look, at x equals 1, we have that value. The limit is saying what are the y values as you get closer and closer to 2. So I got 0 0.2, 0 0.21, 0 0.217, 0 0.22. If I get to x equals 2, it says undefined. Because if you were to plug in 2 into this function, you get a divide by 0 problem, right? But at 1.95, when we're really close to 2, we have 0.24. A little bit to the right, we have 0.26. So it looks like the limit is 1/4, 0.25. We can confirm that algebraically, though, because look, you can factor the numerator in the denominator. Okay, so the limit as x approaches 2 is what we're still trying to evaluate. The numerator can be factored. We need to find two numbers that multiply to be 2, but add up to be negative 3. Okay, we start off the parentheses with our t variable. And then we're trying to find two numbers that multiply to be 2, but add up to be negative 3. And once you think about it for a while, the pair is negative 1 and negative 2. I said those backwards, but negative 2 plus negative 1 makes negative 3. Negative 2 times negative 1 makes positive 2. So that's the pair that we need to factor. And then the bottom, t squared minus 4, you've got t minus 2 and t plus 2. This is one of those special forms of factoring. You need to find two numbers that multiply to be negative 4, but add up to be 0 so that the middle term cancels out. So negative 2 and positive 2 add up to be 0. Negative 2 times positive 2 makes negative 4. Okay, and the whole point of factoring is because, look, the entire numerator is factored, so it's just one term. This can cancel out with this in the denominator. Now, do you have a divide by 0 if you plug in 2? You can just plug it right in now. We can do it by substitution. So the numerator becomes 2 minus 1 is 1. The denominator is 2 plus 2 is 4. So there's the confirmation algebraically that it should be 1/4. And now we've finished evaluating the limit algebraically. So same thing for this one. Look, the numerator and the denominator, you can factor out an x. You can factor out an x squared from the numerator. You can factor out an x squared from the denominator. We have to do something because right now we can't plug in x equals 0. We get a divide by 0 error. So let's factor out that x squared from the numerator. And then from the denominator, x squared as well. So the x squareds cancel. Now do we have a divide by 0 error? If you plug in 0 here, 3 times 0 makes 0. 0 minus 16 is negative 16 in the denominator. And the numerator, 5 times 0 is 0. 0 plus 8 is 8. So if we plug this in a graph, we expect negative 1/2 to be the value when x equals 0. So let's see if I can remember all that. 5x to the third plus 8x squared. I'm off screen here, but I'm just typing in decimals. 5x to the third plus 8x squared, and that's all being divided by 3x to the fourth minus 16x squared. 3x to the fourth minus 16x squared. Okay, so here's the graph, and if we follow this graph as we approach our limit, x equals 0. Oh, did I do something wrong? I'm getting something close to negative 1/2. Oh, no, that's what I got. Okay. Right, so we confirmed it algebraically. As x gets closer to 0, the y values get closer and closer to negative 1/2. And that's from both perspectives. If you approach 0 from the left and you approach 0 from the right, you're getting the same thing. Okay, this one, I'll skip the graph. I'll just do it algebraically. Divide by 0 problem again. Can't plug in 0. But if you expand the numerator, you'd have to do, here, I'll do it off to the side here. 1 plus x to the third means 1 plus x times 1 plus x times 1 plus x. And we subtract 1 from it. And so if I multiply these two together, I'm going to get x squared plus 2x plus 1. And then if we multiply this times this, then we get x to the third. I'm doing x to the third plus x squared. Now I need to make this multiply to both those terms. So it's going to be 2x squared plus 2x, and then plus x plus 1 minus 1. And look, that's because the book is setting these problems up to make it so that you can factor out 1x. Look, these cancel, right? And so every term in here has at least 1x to give, so I can factor the numerator. Oh wait, we could clean it up too. I'll do both those at the same time. We have x to the third divided by x gives us x squared. We had 3x to the second divided by x squared makes 3x. And then we have 3x divided by x makes 1 all over x. So those cancel out. So this is what we're left with. We just rewrote this entire expression, and we just found out that it is algebraically equivalent to x squared plus 3x plus 1. No divide by 0 problem, right? We can just plug in 0, and if you do, you get out 1. So that's our limit. And you'd see that if you graph it. Now you might be wondering, like, why doesn't Desmos pick up on that? Why doesn't Desmos say 1 if I click on x where x equals 0 on the graph? And that's because by definition, this original function had a divide by 0 problem. So 0 is not in the domain of this function. Even though you can algebraically rewrite it like this, the way we've stated it excludes 0 from the domain. Okay, now the book has these two problems too, but I don't know how to algebraically rewrite these. You can't make the x cancel out. So I think the only way you can do this is graphically. So the instructions for confirming algebraically, I think they don't apply. And I'm looking in the teacher's book, and maybe there's something I missed about how you could do some sort of crazy thing to make an x come out of a trig function, but you can't. The x is stuck in some sort of trig function jail. If you do y, no, that's not going to work either. I don't know. Still thinking. We could set this equal to y and use arc sine to both sides. So inverse sine. No, that's not going to work either. I think you can only do these graphically. So let's go to the graph. Sine 2x over x. It's got a divide by 0 problem. So sine 2x over x. If you trace the graph and get closer and closer to x equals 0, it's approaching 2, right? At the actual point of 0, it's undefined because 0 isn't in the domain, but the limit is approaching 2 is what we'd say graphically. Sine squared x over x. Sine squared x over x, and I think that's the limit as x approaches 0. Yeah, we get infinitely close to 0 as x gets infinitely close to 0. We get a y value of 0 that comes out. So that is 0 as well. Remember, the limit is the y values as x approaches some number. As x approaches 0, the y values are getting infinitely close to 0.